Welcome back. I hope you enjoyed the first 2 weeks of class. As I mentioned at the beginning of last week, in these 2 weeks, weeks 2 and 3, we'll cover the fundamentals of two-dimensional signals and systems. Last week, we carried this analysis in the spatial domain, while this week we'll move to the frequency domain. We use two-dimensional signals and systems in our presentation. However, all the information we provide is also applicable to one-dimensional signals, but also to higher dimensional signals, that is, multidimensional signals in general. Thanks to Joseph Fourier, who lived in the late 18th, early 19th century, we can describe any signal of any dimensionality and the operations of any linear and spatially invariant system in the frequency domain. The frequency domain is mostly familiar to us when we refer to one-dimensional signals. For example, we can distinguish between a baritone and a soprano, or between low and high frequencies in a music piece. Images have similarly low and high frequencies, which you cannot hear, of course, but you can see. They are spatial frequencies. We'll get familiar with the concept first, and then we will take the material and the operations of LSI systems we learned last week to the frequency domain. We'll also understand what is involved when we convert a continuous signal to a discrete signal, what we called in week 1 sampling. And also when we change the size of an image, when, for example, we want to display a large image on a small screen of our cell phone, or a thumbnail image on a large screen. And this is called sample rate conversion. Equipped with this material, you can understand what will follow in this class, but also when you are interested in learning new material outside this class, as for example, what's the process of acquiring an MRI image or an X-ray image of a slice of a patient's body using computerized tomography. It's referred to as CT or CT scan, a term you might have heard before. In this first segment, we'll define the two-dimensional continuous Fourier transform of a two-dimensional discrete signal, and we will discuss some of its important properties. We will then work out a number of examples which will give us a good understanding of what constitutes a low-pass and what constitutes a high-pass filter. We'll finally talk about the important convolution theorem, which states that the convolution operation in the spatial domain becomes a multiplication operation in the frequency domain. So let us start covering this important material. Let us consider a linear and spatially invariant system with impulse response h, n1, and 2. We put in signal x as its input, and this signal is a complex exponential with specific frequencies omega 1 prime, omega 2 prime. This is a two-dimensional pure tone since it only contains, again, this particular frequency omega 1 prime, omega 2 prime. We want to find out what the output of the LSI system to this particular input is equal to. I did mention at some earlier point in the course that these complex exponentials are eigenfunctions of LSI systems, which simply means that such complex exponentials go through the system without their frequencies being altered. Of course, by now we know how to find the output of an LSI system. It's yn1 and 2 is equal to the convolution of the input to the system with the system's impulse response. If I apply directly the definition of the convolution, this is equal to this double sum. Again, I just applied the definition of the convolution. Now we see that these terms are independent of k1, k2, therefore they can come outside the summation, and all I'm left with is are these terms here. So we see that the complex exponentials appear at the output of the system. They just went through the system, and this term here tells me how the system responded to this particular complex exponential at these specific frequencies. This here is a complex quantity. It has a magnitude and a phase, and we see that the LSI system is able to discriminate among sinusoidal signals on the basis of their frequencies. So if the magnitude of this term here is equal to 1, then the sinusoidal, the complex exponential, goes through the system unchanged, while on the other hand, if the magnitude is equal to 0, the complex exponential is rejected by the system. So therefore, this is the response of the LSI system with impulse response hn1 and 2 at these frequencies omega 1 prime, omega 2 prime, or denoted by capital H, omega 1 prime, omega 2 prime, and this is the frequency response of the system. Now, since this result is not going to change if I consider additional frequencies, let's say omega 1 double prime, omega 2 double prime, we have that this is again the response of the system at any frequency, and this capital H omega 1 and omega 2 is the Fourier transform of the impulse response of the system Hn1 and 2. We're going to say considerably more things about the Fourier transform in the next slides. We show here the two-dimensional Fourier transform pair. This is here the expression for the forward transform that will take an image from the spatial domain and map it to the frequency domain, where omega 1, omega 2 are continuous variables. So x omega 1, omega 2 is the two-dimensional Fourier transform, or the spectrum of the image x and 1 and 2. This is the expression of the inverse Fourier transform that will take us from the frequency domain back to the spatial domain. We see with the expression on top that even when the image is real, as is usually the case, the Fourier transform is complex due to the presence of these complex exponentials. Therefore, in representing it, I can show the magnitude and the phase of the Fourier transform. And this represents the polar representation of a complex number, or equivalently, I can show the real and imaginary parts. I see here in the expression for the inverse Fourier transform that we integrate from minus pi to pi in the omega 1 and minus pi to pi in the omega 2 directions. And this is due to the first property of the Fourier transform, that it is periodic with periods 2 pi in the omega 1, omega 2 directions. This is a straightforward expression to show. In essence, we showed it when we studied the complex exponentials. We saw that they're periodic with period 2 pi, and this is what gives rise to this property. Another useful property is to consider what happens when I shift the image by amounts m1, m2 in the spatial domain. And what happens in the frequency domain is I get the spectrum of the signal, but it's multiplied by this complex exponential. So since the magnitude of the complex exponential is 1, the magnitude of the shifted image has not changed, but I have this linear phase component that is due to the spatial shift. The reciprocal to this property is the modulation property that tells me what happens if I shift the spectrum by theta 1, theta 2. So similarly, I see that I have this complex exponential appearing in the spatial domain. Another useful property is this, which is typically referred to as the Hermitian property, which tells us that when the signal is real, then the magnitude of the Fourier transform has even symmetry, while the phase of the Fourier transform has odd symmetry. And finally, this is the Parseval's relation or theorem, which tells me that the energy of the signal, which is found according to this expression in the spatial domain, can also be found in the frequency domain by integrating over one period to pi this energy density spectrum. There are clearly additional properties, quite a few of them, that one can find in a standard image processing textbook, but these are some of the more useful ones. Let us consider a simple example. We are given a system with the impulse response depicted here, and we want to find the frequency response of this system. So we apply the definition of the Fourier transform, and the frequency response is equal to this double summation h n1 and 2 e to the minus j omega 1 and 1 e to the minus j omega 2 and 2. Now for the given impulse response, we see that we have only 5 samples. So we have the h minus 1 0 sample, h0 0, h1 0, h0 minus 1, and h01. So out of this infinite sum, I only have these 5 terms. So h00 multiplied by e to the minus j0, which is 1, plus h minus 1 0 multiplied by this term, and now I substitute the given values of h. So this is 1/3, and all the rest are 1/6. So equal to 1/3. Now we observe here that due to Euler's formula, e to the plus j omega 1 plus e to the minus j omega 1 will give me 2 times cosine omega 1. And similarly, the other 2 terms will give me 2 times cosine omega 2. And I can further simplify this as 1/3, 1 plus cosine omega 1 plus cosine omega 2. So we see that for this particular example, the frequency response of the system is real. This should come as no surprise, since one of the properties of the Fourier transform is that if the signal has even symmetry, then the Fourier transform is real. This means that the magnitude is the absolute value of this term, and therefore the phase is 0 at all frequencies except when this term here becomes negative, in which case I have a plus or minus pi phase jump, since minus 1 has absolute value 1 and phase plus minus pi. So let's see how this frequency response looks like. So I plot here the magnitude on the vertical axis, and I show it over one period, omega 1 from minus pi to pi and omega 2 from minus pi to pi. This actually magnitude has even symmetry, which is also should come as no surprise, because we saw in the previous slide that one of the properties of the Fourier transform is that if the signal is real, then the magnitude has even symmetry and the phase odd symmetry. So if I look at this magnitude, I see that h00 is equal to 1, right? Cosine 0 is 1, so I have 3/3. And also I observe that at certain frequencies, the magnitude becomes exactly 0. So for example, if I look at the frequency minus pi over 2, I have 1 plus cosine minus pi, which is minus 1, so they cancel out, 0, plus cosine at pi over 2, which is 0, and therefore this is 0. This is actually the frequency over here, right? So by and large, this is a low-pass filter. It passes the 0, frequency unchanged, attenuates slightly the low frequencies, but as the frequencies increase, the attenuation becomes greater. We show here an example similar to the previous one. We're given the impulse response of a system, and we're interested in finding its frequency response. The form that HN1 and 2 is depicted is slightly different from the previous case. It's shown here as a 3x3 matrix. It should be understood that this is the H00 sample, this one the H11, while let's say this one is the H-11, and so forth. This actually approximates a Gaussian shaped function in this 3x3 window. After a point, when you look at this impulse response, which is again has symmetric, has even symmetry, one should be able to identify terms in the frequency response. So for example, this and this term should give rise in the frequency response of a 2 times cosine omega 1 times the coefficient, while the diagonal terms, this term and this term, should give rise to a term like this in the frequency response, 2 times cosine omega 1 plus omega 2. So if you work out the example, you should find out that this is the frequency response of this system as shown here. It's again a real signal, which should come as no surprise because HN1 and 2 has even symmetry. If we plot the magnitude of this term, it looks like this. Here I plot on the vertical axis the 10 times log base 10 of the magnitude, so one can see more clearly small values of the magnitude of the frequency response. Again, if I look at H00, this is the sum of the values of the impulse response, and they sum up to 1, and therefore the logarithm of this value is equal to 0. So this term here, that's the 0, it's equal to 0. We see again that this is a low-pass filter. It attenuates slightly the low frequencies and considerably the higher frequencies. And of course, the 0 frequency goes through the system unchanged of the input signal. Here's a final example. We're given a system with impulse response depicted here, and we want to find its frequency response. The comments I made earlier apply here as well, so this is the H00 sample. We see actually that this impulse response differs in some sense from the previous ones, in the sense that I take differences now between the center sample here 9 and the neighboring sample, so we should expect that the shape of the frequency response should be different. So following exactly the same steps that we followed in the previous 2 examples, one can find that the frequency response of this filter of this 2D system is shown here. It's real again because HN1 and 2 has even symmetry. If I plot this, so I plot here the magnitude in the vertical dimension, and I plot again the 10 log 10 magnitude, so that I'm able to see smaller differences. We see that now the shape is different in the sense that the low frequencies are attenuated while the high frequencies are amplified. We can easily see that the H00 is equal to 1, and therefore the log of this is equal to 0. While if I look at some frequencies, for example the H0 pi frequency, which is the frequency over here, this is equal to 13, while the H pi pi is equal to 9. So considerably higher values than 1 at high frequencies and small values at 0. again, low frequencies are attenuated, high frequencies are amplified, high spatial frequencies in an image are represented by the edges. Therefore, the edges are allowed to go through this system while the flat regions are rejected or greatly attenuated, and therefore a filter like this performs edge detection on an image. One of the important properties of the Fourier transform is the convolution property, or as also referred to, the convolution theorem. It describes the input-output relationships of an LSI system in the frequency domain. So given a system with impulse response H and X in the input, Y the output, we know that the input-output relationships in the spatial domain are through the 2D convolution. So the output equals the convolution of the input with the impulse response of the system. Clearly, I can take each of these quantities to the frequency domain. So I can find the spectrum of the signal. I can find the Fourier transform of the impulse response, which is the frequency response of the system. And I can find the Fourier transform of the output signal. Since these signals are clearly related in the spatial domain, one expects that they should be related in the frequency domain. And what the convolution theorem tells us is that indeed the spectrum of the output signal equals the spectrum of the input signal times multiplied by the frequency response of the system. So convolution in the spatial domain becomes multiplication in the frequency domain, and actually the reverse is also true. Multiplication in the time domain becomes convolution in the frequency domain. Of course, here we have to talk about periodic convolution since the signals are periodic. So let's see that indeed this is the case. So if I write the output of the system as the system T, let me call the system T operating on the input signal X and 1 and 2. And then I'll replace the signal by its inverse Fourier transform. So this is equal to this double integral of x omega 1 omega 2 e to the j omega 1 and 1 e to the j omega 2 and 2 d omega 1 d omega 2. Actually, the inverse Fourier transform tells me that you can think of any signal x and 1 and 2 as the weighted sum of these complex exponentials, where the weights are indeed the values of the Fourier transform. Now, since the system is linear and assuming all the signals here are well defined, I can interchange the order of integration and the operation of the system. And the system operates on signals that are functions of n1 and 2. Therefore, the Fourier transform, the weights as I call them, are constants as far as the system is concerned. So I am left with this expression. Now we have studied the expression, we know that these complex exponentials are eigenfunctions of LSI systems. So they go through these systems unchanged and they're multiplied by the frequency response of the system. So therefore, this expression becomes equal to this one. So it's the frequency response of the system times the complex exponentials. So now this is the expression for the inverse Fourier transform of y, and therefore this signal here is the Fourier transform of y. So this is y omega 1 omega 2. So indeed we showed that y omega 1 omega 2 equals x omega 1 omega 2 times the frequency response of the system. We alluded to this operation when we talked about the example, so therefore all this tells me is that looking at the frequency response of the system, I have to just process each frequency one at a time, right? So if h here is 0 at certain frequencies, then the output y is going to be 0. Therefore, those frequencies of the input signal will not go through the system.